In this video, we look at how we can use 2x2 matrices and 3x3 matrices to describe transformations in 2 dimensions. As far as the specification is concerned, we are told that we must be able to use matrices to represent linear and non-linear transformations in 2 dimensions, and we must be able to deal with successive transformations. We must also be able to find invariant points or fixed points, and also fixed lines or invariant lines for linear and non-linear transformations. So let's have a look at the key facts then. If we have a transformation described by the point xy going to ABCD times by xy, then under that transformation, the image of the origin will always be the origin. The image of the point 1, 0 is given by the first column of the matrix. It's the point AC. And the image of the point 0, 1 is BD. The point is given by the second column of the matrix. There are 2 really important examples of transformations given by 2x2 matrices. And that is for the rotation of theta degrees anti-clockwise about the origin, has a matrix whose first column is cos theta sine theta, and whose second column is minus sine theta cos theta. And the second really important one is that a reflection in the line y equals tan theta times x can be described by the matrix whose first column is cos 2 theta sine 2 theta, and whose second column is sine 2 theta minus cos 2 theta. And these 2 results are given in the formula booklet. It's important to realise that if we have a transformation S, whose matrix is A, and a second transformation T, whose matrix is B, then the transformation S followed by T will have the matrix B times by A. And notice that the order is B, that's the transformation for the matrix for the second transformation, times by A, the matrix for the first transformation. If we need to find the image of a line under a matrix transformation, we can do that by setting up a general point P on the object line in terms of a parameter. We then find the image of that general point under the transformation in terms of the parameter. And then finally we can find the equation of the image line by eliminating the parameter from the equations for x dash and y dash to obtain a single equation linking x dash and y dash. And we'll see this process in practice in the first example that we look at. 2x2 matrices can only be used for transformations that leave the origin fixed. Now it's obvious that a translation will not leave the origin fixed, and therefore we need a subtly different way of handling transformations that involve translations. So if we think about the translation given by P in the x direction and Q in the y direction, then that translation can be written using a 3x3 matrix by saying that the point xy goes to the point x dash y dash, where x dash y dash 1 is obtained by multiplying the 3 by 3 matrix whose first row is 1, 0, p, whose second row is 0, 1, q, whose third row is 0, 0, 1, by the column vector x, y, 1. And with pushing that a little bit further, you will have seen that the transformation x, which takes xy to x dash y dash, where x dash y dash 1 is obtained by taking the 3 by 3 matrix whose first row is ABP, whose second row is CDQ, and whose third row is 0, 0, 1, times the column vector xy1, gives us a transformation equivalent to, first of all, the 2 by 2 matrix ABCD, followed by the translation with vector PQ. For any transformation, the point alpha beta is a fixed point of the transformation if the image of the point alpha beta is alpha beta. So if T is represented by a 2 by 2 matrix, then we've got the matrix times alpha beta must equal alpha beta. And if the transformation is represented by a 3 by 3 matrix, then we've got the matrix times alpha beta 1 must give me alpha beta 1. A line L is a fixed line of a transformation if the image of the line L is itself the line L. So now let's have a look at our first example. So we have a transformation T consists of an anti-clockwise rotation through 45 degrees about the origin, followed by a reflection in the line x plus y equals 0. And the first thing we have to do is justify that the matrix T is the one given in the question. So, if we remember the results that are actually given in the formula booklet, then we can see that an anti-clockwise rotation of 45 degrees about the origin is going to be represented by the matrix whose first column is cos 45 sine 45 and whose second column is minus sine 45 cos 45, in other words by the matrix 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. Moving on to think about the reflection, well, the line y plus x equals 0 is the same thing as y equals minus x, which is the same thing as y equals the tan of minus 45 times by x. So using the second of the two results, which are given in the formula booklet, we can say that the matrix for the reflection must have a first column, which is cos of 2 times minus 45, sine of 2 times minus 45, and a second column, which is sine of 2 times minus 45, minus cos of 2 times minus 45. So the matrix B, which is the matrix of the reflection, must have a first column of 0, minus 1, and a second column of minus 1, 0. We know that the matrix for the rotation followed by the reflection will be the matrix for the reflection times by the matrix for the rotation. Got to be careful on the order of this. If we perform the matrix multiplication, we get first column of minus 1 over root 2, minus 1 over root 2, second column minus 1 over root 2, 1 over root 2, which is precisely what we were being asked to prove. Moving on to the second part of the question, we have to find now the equation of the image under t of the line y equals mx. Now, a typical point on the line y equals mx might have an x-coordinate of alpha and a y-coordinate of m times alpha. If we find the image of this point by taking the matrix of the transformation and multiplying it by alpha m alpha, then we obtain 1 over root 2 times minus alpha minus m alpha minus alpha plus m alpha. So if x dash y dash is the image of the point alpha m alpha, then we have x dash is 1 over root 2 times minus alpha minus m alpha. Tidy that up a little bit. We've got x dash is minus common factor of m plus 1 over root 2 times by alpha. And y dash similarly is m minus 1 times alpha over root 2. So we know what x dash is in terms of alpha. We know what y dash is in terms of alpha. But what we really want is the equation of the image line. So we need to eliminate the parameter. We need to eliminate alpha from these two equations that we've got. And that's done fairly easily. If we take the equation for y dash and divide it by the equation for x dash, we're going to obtain y dash divided by x dash is m minus alpha divided by minus m plus 1. In other words, we have got y dash is m minus 1 divided by minus m minus 1 times x dash. So we've got our image line is y dash equals m minus 1 over minus m minus 1 times by x dash. Now, if the object line is transformed into itself, then the gradient of the object line must be the same thing as the gradient of the image line. The gradient of the object line is m. The gradient of the image line is m minus 1 divided by minus m minus 1. So we must have m equals m minus 1 divided by minus m minus 1. Multiply up by minus m minus 1 to clear the fractions. And then get everything on one side, so we've got a quadratic equation. We've got 0 equals m squared plus 2m minus 1, which means that m is minus 1 plus or minus root 2, by whichever means you want to solve your quadratic equation by. Let's now move to a second example. And in this case, we've got the transformation t consists of an anti-clockwise rotation through 90 degrees about the origin, followed by a translation in which the point xy is moved to the point x minus 3, y plus 1. So the first thing we've got to do is show that the matrix representing t is the one given in the question. Well, again, if we go back to the results that we've got in the formula booklet, we can very quickly deduce that the matrix for a rotation through 90 degrees anti-clockwise has got to be the matrix whose first column is cos 90 sin 90, whose second column is minus sin 90 cos 90. So the matrix of the rotation must be first column 0, 1, second column minus 1, 0. So we've got the matrix for the rotation, which means that our arbitrary point xy, once we've done the rotation, will become the matrix times by xy, which gives me minus yx. Now the translation that we've got is a translation of minus 3 in the x direction and 1 in the y direction. So once I take the point minus yx and translate it by minus 3, 1, I'm going to end up with minus 1 y minus 3 x plus 1. So the point xy is being transformed to the point minus y minus 3 x plus 1. If we're using a 3 by 3 matrix, we're going to have to say the column vector xy1 becomes the column vector minus y minus 3 x plus 1, 1, which we can write as a matrix multiplication of the matrix with first column 0, 1, 0, second column minus 1, 0, 0, third column minus 3, 1, 1, times by xy1. So the matrix for the transformation is this matrix here, 0, 1, 0, minus 1, 0, 0, minus 3, 1, 1. We've now got to find the coordinates of the fixed point of t. So let's suppose that alpha beta is a fixed point of t. Then that means that the matrix times by alpha beta 1 must equal alpha beta 1. In other words, we've got minus beta minus 3, alpha plus 1, 1 must equal alpha beta 1. So we have some simultaneous equations here. We've got, looking at the x coordinates first of all, we've got minus beta minus 3 must equal alpha, which I can rapidly rewrite as alpha plus beta plus 3 equals 0. And I've got alpha plus 1 must equal beta, or 0 equals beta minus alpha minus 1. If we add those two equations, we're going to get 2 beta plus 2 equals 0. So beta must be minus 1. And if beta is minus 1, then alpha must be minus 2. So the fixed point is the point minus 2, minus 1. Finally, we're told that the image of the line L under the transformation t has got equation x plus 2y equals 3. And we have to find the equation of L. So let's suppose that the point xy is mapped by the transformation t onto the point x dash y dash. Then we have x dash y dash 1 must be the matrix times by xy1, which we already know gives me minus y minus 3 x plus 1, 1. If So we've got, if that means that we've got x dash equals minus y minus 3 and y dash is x plus 1. Now, if the image point lies on the line x plus 2y equals 3, that means that we have got x dash plus 2y dash must equal 3. Which means that we've got minus y minus 3 plus 2 lots of x plus 1 must equal 3. Which means that the original point, xy, must satisfy 2x minus y equals 4. Finally, let's just look at this example. We've got rotation t has the matrix given there, and the first thing we're being asked to do is to find the coordinates of the fixed point of t. So it's very similar to the example we've just done. Let's suppose that alpha beta is the fixed point. Then we've got the matrix times alpha beta 1 must equal alpha beta 1. So, looking at the x-coordinate first of all, that means I've got 0.6 alpha plus 0.8 beta plus 2 must equal alpha. And we must also have minus 0.8 alpha plus 0.6 beta plus 3 equals beta. Collect all the alpha and betas on one side and the numbers on the other side. So we've got 2 is 0.4 alpha minus 0.8 beta. 3 is 0.8 alpha plus 0.4 beta. Solve the simultaneous equations. We've got alpha equals 4, beta equals minus 0.5. So the fixed point is the point 4 minus 0.5. Now we're told that this transformation is a rotation. Rotation only has one fixed point, and that fixed point is the centre of the rotation. So straight away at this stage we can write down that the centre of the rotation is the point 4 minus 0.5. A quick sketch diagram will help us to think about the angle of the rotation. So we know the centre of the rotation is the point 4 minus 0.5. So what we'll do is we'll just take a point which is really conveniently connected to the centre of the rotation. We'll take a point which is 1 unit away in the x direction. We'll take the point 5 minus 0.5. The matrix multiplication tells me that the point 5 minus 0.5 is transformed to the point 4.6 minus 1.3. So, a little sketch diagram now. I've got the centre of the rotation as the point 4 minus 0.5. If I start off with the object point being 5 minus 0.5, then the image is the point 4.6 minus 1.3. So the angle of the rotation is the angle theta in the diagram. And if we just make a right angle triangle out of that, then we have got a y step there of minus 0.8 or 0.8 downwards, and we've got an x step there of 0.6. So we've got tan theta is 0.8 divided by 0.6. So theta is 53.1 degrees. So the rotation is a clockwise rotation of 53.1 degrees.